Now the next thing we want to do is just to generate the frequency distributions, and these basically are what Jed showed you in class in his video. And our bins are going to represent the number of survivors in a particular trial, and we'll stretch this number down to 25. So the idea here is we want to just summarize the results of these 100 trials. So under column I, we're going to be creating a histogram. So how many times out of those 100 trials did we end up with 0 survivors? How many times did we end up with 1 survivor? And so on. So for example, here's the number 7. We would want to tally that in this cell here. 2 more 7s, that gives us 3 7s, so we'd have the number 3 here. Here's a number 4, we would tally it here. Make sense? We can do this very quickly with a frequency function in Excel. And let me show you how that works. The frequency function is a little bit different than other functions because it's called an array function. Now with an array function, you need to highlight a whole bunch of cells at one time. So I'm selecting all of my cells, and then I'll head up to the Insert Function button and I'll find frequency. This particular function has 2 arguments. The first is the data array, and for this case I want to grab my results that are associated with the population size of 10. And the bins array are just the groupings that I'd like to store my data in. Those are stored down cells H17 through H42. Now whatever you do, don't press OK. If you've pressed OK, you might want to start this over again. Because this is an array function, you need to press Control, Shift, and Enter in order for this function to calculate correctly. I like to go up into my formula bar and click in it, and then press Control, Shift, and Enter. And you can see then that Excel calculates all of our results and generates this frequency histogram. So we have frequency on the vertical axis, and we have number of survivors across the horizontal axis. Let's do the same thing for the case where we had 25 individuals. We'll select our cells. We'll go to the frequency function. Our data array in this case are the trial results stored down column G. And the bins array will be the same array that we used before. We won't touch OK. We'll head back up to the formula bar and press Control, Shift, and Enter. And now we have a second histogram added in. Now at this point, we have basically recreated the histogram that Jed showed in his video. When we're dealing with a small population size, here's the range of outcomes we have. In my particular case, I didn't have any with 0, 1, or 2 survivors. So my data looks like this. Your results may look different, and that's fine. That's because you have drawn different random numbers than I have. The results for the population size of 25 span more. And if you look at these, you can see that the red results have a greater range than the blue results. Let's go ahead and characterize these 2 distributions by recording their mean and their standard deviation. So the mean is just the average function. So we'll choose the data for population size of 10. And then we can just copy this over to get the simulation for the population size of 25. The standard deviation we can also compute. That is going to be STDEV .s, and that stands for calculating the standard deviation based on a sample of data, which is what we have here. And again, we'll do this for the, calculate it for the population size of 10. And we can pull it over to calculate the population size of 25. So in fact, you can see exactly what Jed was pointing out. Here, the mean for the population size of 10 is about 6 survivors. The standard deviation, though, is 1.43, so it's lower. The mean number of survivors for the population size of 25 was 14.26, and the standard deviation is bigger. So that's just reflected in the spread of data here. Now, before we go on, though, I want to point out something really important, and that is that these mean values are pretty close to what we expected because we modeled this population with a survival rate of 0.6. So we ran 100 trials, and on average, we're getting very close to 6 survivors when the population size is 10. And we'd expect that, right? If there are 10 individuals and 60% of them will survive, then we expect there would be about 6 survivors. And here, for the population size of 25, we expect that there would be 60% of these 25 individuals surviving, and that's 15. So this is a little bit lower than what we'd expect, but it's pretty close. So our mean value is pretty much very close, very spot on. And that's because we modeled the population with this fixed rate here. What's different, though, is the standard deviation. And as Jed pointed out, when you look at the range of data, here's the population size of 10. This had a range of data that could go between 0 and 10. And we see that it pretty much takes up as much space as there are options. For the example where there are 25 individuals, though, we could have had 0, 1, 2, 3, 4, 5, 6, all the way up to 25 survivors. But we don't see the red distribution taking up that full space. Instead, we see it constrained mostly between, say, 7 and 21. And the way to compare these two distributions is to look at the standard deviation and then adjust them by the mean. And we do that by just division. We'll take the standard deviation, divide it by the mean, and we'll carry that over, and that is our calculation of the coefficient of variation. This is what Jed talked about in lecture, and this is the key point. When you correct and look at the variation from the standpoint after you adjusted by the mean, you'll see that the smaller population, here 10, has more variation compared to the larger population. And that's strictly a function of our population size being small. Now you can feel free to explore what would happen if the population size was, say, 50. Would you expect this number to change and continue to shrink, or would it perhaps level off at some point? Those are things that we can explore in the sandbox. Now you might be noticing and wondering what this binomial distribution section is. And really, whether you know it or not, when we do this equation, when we entered this equation to determine if individual 1 survived using this if function, we actually were using a special case of the binomial distribution. And we'll talk about the binomial distribution and other statistical distributions that could be used to simulate data for populations to really explore demographic stochasticity in different ways. That's on a separate video, so for now, we'll turn you back over to Jed, and we'll see you next time.
Great, thank you, Terry. I hope that spreadsheet exercise was really helpful in your understanding of demographic stochasticity. So we've covered a fair amount of ground in this module, and just as a quick wrap up, here are a few of the main points. Stochasticity is random variation. And demographic stochasticity, the focus of this module, is this variation that we see in average survivorship and reproduction due to the fact that individuals in a population are integers, really. We can model the effect that demographic stochasticity can have on populations, and in order to do that, we need to know really what the initial size of our population of interest is, and we need to know something about birth rates and survivorship, which is in many ways a function of death rates, for example. When we model demographic stochasticity, it becomes quite clear that small populations are very susceptible to it. In other words, demographic stochasticity has a much more pronounced or magnified effect on small populations versus large populations. What kind of effects do we see? We see very unpredictable changes, let's say, in the way that population changes from one year to the next, and in some cases it can result in complete extinction of that population. So as such, it's an important consideration when we're managing species, especially those that live in small populations, those that may be rare, threatened, or endangered. So I hope at this point you've got a pretty good understanding of what demographic stochasticity is, how you might be able to model it, and why it's important from a management or conservation point of view.